Thanks to pioneering therapy, a paralyzed man regained his ability to walk. A man who had been paralyzed for over a decade got back on his feet. All thanks to 2 implants that restored communication between the brain and the spinal cord. New research gives hope to paralyzed people after spinal injuries to regain the ability to move. 12 years ago, as a result of a bicycle accident, Gert-Jan Oskam suffered a cervical spinal cord injury. Since then, he has been unable to move his legs. And some paresis has also affected his upper limbs. But the now 40-year-old man got back on his feet and regained his ability to move. All thanks to devices that created something like a digital bridge between his brain and spinal cord, restoring the connection broken during the injury. The implants used in the new therapy are the latest work of a team of neurobiologists from Switzerland. Their research has amazed the world many times. In 2018, they brought 3 paralyzed men to their feet using precise electrical stimulation to stimulate the nerves of the spinal cord via a wireless implant. In 2022, they helped 3 more people regain the ability to walk, who were completely paralyzed from the waist down due to spinal cord injuries. Swiss scientists have also identified a group of nerve cells that are crucial in the process of regaining mobility by paralyzed people. The description and results of the latest research have been published in the journal Nature. Scientists from the Federal University of Technology and the University Hospital in Lausanne, in cooperation with scientists from other institutions, have been conducting research on restoring motor functions to people after spinal injuries for years. To this end, they are developing brain-computer interface technology that can use wireless signals to re-establish communication between the brain and the spinal cord. The device used in the new research builds on earlier work by neuroscientist Grégoire Courtine and his team at the Federal Polytechnic University of Lausanne. In 2018, researchers showed that when combined with intense training, technology that stimulates the lower spine using electrical impulses can help people with spinal cord injuries regain their ability to walk. Oskam had participated in earlier studies by Swiss specialists that included epidural spinal cord stimulation combined with a rehabilitation program. Electrodes were implanted into his spinal cord, which delivered electrical impulses to stimulate the nerves. This allowed him to walk, but the process was difficult and frustrating. Now, researchers have offered Oskam a better solution, digitally bridging the communication gap between his brain and lower body. Brain waves signaling Oskam's willingness to walk travel wirelessly from a device implanted in his skull to a spinal stimulator, redirecting the signal around the injury and delivering electrical impulses to the spinal cord to facilitate movement. In other words, when Oskam thinks about walking, the skull implants detect electrical activity in his brain. This signal is transmitted wirelessly and decoded by a computer that Oskam carries with him, which then sends the information to a pulse generator on the spinal cord, which delivers different patterns of electrical pulses depending on the desired movement. Oskam can now walk more smoothly, overcome obstacles and even climb stairs. The previous device, Courtine admitted, was more of a programmed stimulation that generated robotic movements. Now it's completely different because Oskam has full control over the stimulation parameter, which means he can stop, he can walk, he can climb stairs. We have created a wireless interface between the brain and the spinal cord that transforms thought into action, admitted Courtine. Before, the stimulation controlled me. And now I control the stimulation. When I decide to take a step, the simulation will run as soon as I think about it, Oskam noted. We implanted devices over the area of the brain responsible for controlling leg movements. These devices decode the electrical signals generated by the brain when the patient thinks about walking. We also placed a neurostimulator connected to an array of electrodes over the area of the spinal cord that controls leg movement. Explained neurosurgeon Jocelyn Bloch of the University Hospital of Lausanne. The devices installed on the skull are two systems containing 64 electrodes each. They are located above the motor cortex and intercept signals from the brain. The devices have been in operation for more than a year, allowing Oscom to stand, walk, climb stairs and navigate complex terrain that would never have been possible before. After approximately 40 rehabilitation sessions using the interface, Oscom regained the ability to move his legs and feet freely, a type of movement not possible with spinal stimulation alone, and suggests that training sessions with the new device resulted in the regeneration of nerve cells that had not been completely severed during the injury. What's more, the rehab worked so well that Oscom can also walk short distances with his implants disabled if he uses crutches. The authors of the study emphasize that it is important to treat this single-participant study as a proof of concept. It is not yet clear whether other people with spinal cord injuries will get similar results. Some injuries can completely sever the spinal cord, but more often than not some broken connections remain between the brain and the lower body. This is still in the early stages of testing and further development of the interface. However, Courtine and Bloch believe the approach can be adapted to other spinal cord injuries, such as those where the arms and hands become paralyzed. Scientists also believe that the developed methods can also be used for people who have been paralyzed for other reasons, such as stroke. Fossil turtle egg from the Cretaceous period with an embryo inside. A group of Chinese and Canadian scientists have discovered an embryo in a fossil turtle egg from the Cretaceous period. What's more, scientists were able to identify the species to which the eggs belonged. They were human-sized land turtles that probably died out in the same catastrophe as the dinosaurs. Tens of millions of years ago, a giant tortoise in what is now central China laid eggs. One of them never hatched and remained undisturbed for tens of millions of years, preserving a tortoise embryo within it. It lay quietly until 2018, when a local farmer came across it and donated it to the local university. The egg was discovered in Henan province, a region where hundreds of fossilized dinosaur eggs have been found over the past 30 years. The results of the new analysis of the ancient egg have been published in the journal Proceedings of the Royal Society B. Biological Sciences. Cretaceous dinosaur and turtle eggs are extremely rare. Their delicate structure makes it difficult for them to survive to the present, even in the best conditions. Finding a petrified embryo in an ancient egg is even rarer. A team of scientists from China and Canada found such a specimen. The farmer who dug up the fossils described them as a few strange-looking rocks. One of these rocks turned out to be a turtle egg with an embryo inside. Scientists have determined its age to be between 66 and 145 million years ago. By examining the egg with various techniques, including computed microtomography, the researchers were able to determine that the egg belonged to the Uschles nanyingensis turtle, a land-dwelling species that became extinct in the same catastrophe that annihilated the dinosaurs. Previous studies have shown that the egg with the embryo inside, and several others found next to it, were quite large. Their mother, the researchers estimated, probably had a shell diameter of up to 1.5 meters. This measurement does not include the length of the neck or head. So the mother turtle had a length comparable to the height of a modern human, the researchers estimate. However, scientists gained more information about the characteristics of these turtles after recreating the embryo using 3D computer modeling. Thus, they found the flat ribs that are characteristic of modern small turtles. As the turtle grows, they form the basis of the shell. Scientists suggest that the ancient tortoise was probably not much different from its modern brethren, with one exception: it had an unusually thick eggshell. As a rule, eggshells are quite thin, both in birds and turtles. This is because the little creature growing inside must at some point get out of the egg and break the shell, having to overcome a wall almost 2 millimeters thick. The young turtle from an ancient egg had to have special abilities to get to the world. The thick shell of the egg allowed water to penetrate. The researchers concluded that the eggs were probably buried deep underground in moist soils so that they would not dry out in the arid environment. While these turtles' terrestrial lifestyle, thick eggshells, and underground nesting strategies may have served the turtles well during the Cretaceous. It's possible that the species failed to adapt to the cooler temperatures and climate and environmental changes that followed the asteroid impact 66 million years ago. The nearly spherical egg measures 5.4 by 5.9 centimeters and is slightly smaller than a tennis ball. It is larger than the eggs of most living tortoises and equal in size to the eggs of elephant tortoises living in the Galapagos. Noteworthy is the already mentioned thickness of the eggshell. It is about 2 millimeters thick, which means that the shell is 4 times thicker than the eggshell of Galapagos elephant turtles and 6 times thicker than the eggshell of a chicken egg, which has an average thickness of 0.3 millimeters. Larger eggs, such as ostrich eggs, have similarly thick shells, but a petrified egg is much smaller than an ostrich egg. The researchers also determined that the embryo was about 85% developed. Part of the eggshell is damaged, which may indicate that the young turtle was trying to hatch. The researchers suggested